All right. Okay. You want to believe that everybody have seen it?
Okay.
Hmm? I can't hear you people now. You are not responding.
We have seen it, sir.
I have seen it.
So is there any question? Or what do you want to do about it?
I have not listened to you, sir. Emil, I have not listened to you.
Yes, the same with me. I just think my today, so my phone was faulty.
What?
I've not been able to do lectures.
You don't?
I said I haven't been able to listen to the lecture as well. I just fixed my phone today. It was faulty. I have to learn the audio and the likes. So I've got through the notes, but
I didn't get the last part.
I said I have went through the notes, but my phone was faulty. The audio, like I just fixed it today anyways. So I've not been able to listen to the video.
But you have gone through the PDF.
Yes, yes, the PDF is. I would say I wanted to believe that maybe if I listen to the notes, it will be more clear. Because judging with people, I don't understand.
And so, based on what you have read or what you have listened to, is there any question?
I want to listen to it first before I. The PDF alone is not comprehended. Yeah.
It's not.
Like going through the PDF alone.
Yes.
I don't want to say we. I don't understand. So
Going
I want
through
to
the
listen
PDF.
to it. I'll listen to it after. Huh?
Your line is breaking. I can't get.
Yeah, problem with it.
Problem with what?
Network. There is network problem here. Not.
I should have go and get. I mean, get to somewhere you think the network is perfect so that you can be able to enjoy the lecture perfectly. Okay. Now, what do you want us to discuss now that we are here?
I think maybe you should just give us an overview of those two lectures, maybe brief. Yeah?
All right. If that is the case, let me see if I can be able to do that within the next 30 minutes.
Yes.
Okay. The lecture is about the factors affecting structure and physical properties of organic compounds. Okay. Let me see if I can share this so that you can see it. Can you see my screen?
Yes, sir.
Yes, sir.
Okay. This is what the lecture is all about. And in the course of the discussion of this factors affecting physical properties, structure and physical properties of organic compounds. Okay, we have this objective. Let me just go to the. Now, one of the points you should know about factors affecting these properties is the intermolecular forces of attraction. If you will recall that molecules, the existence of molecules is predicated on the type of intermolecular force of attraction that is operating within the molecule of that substance. Okay? And you also know that substances exist in three phases. You have the solid, liquid, and gas. For a substance to exist as a liquid, a solid, or a gas depends on the nature of the intermolecular forces. If the intermolecular forces are strong, they are very strong, the substance will exist as a solid. And if the intermolecular forces are weak, if they are very weak, the substance will exist as a gas. Meaning that if you have strong intermolecular forces, it means the intermolecular forces will bring the molecule together firmly. That is why the substance can exist as a solid. But if the forces are weak, the molecule will be able to move apart freely. That's why you have liquid or gas. Also, you should also know that if temperature is raised in a substance, if you raise the temperature of a substance, the molecule will acquire energy to overcome the forces that is binding them together. Okay? That is why when you eat a liquid, after some time, the liquid will start boiling and will change to vapor. That means the molecule in that liquid is gaining energy to overcome the intermolecular forces. Also, if it is a solid, if you eat a solid, the solid, after some time, will start to melt. It will change into liquid. It means also the molecule in that solid is acquiring energy to overcome intermolecular forces of attraction. Now, we have different types of intermolecular forces of attraction. We talk about the van der Waals. Van der Waals, okay. Okay, we talk about dipole forces. Dipole forces is as a result of this dipole in a molecule. If you have a substance such as hydrogen chloride, you know that hydrogen and chlorine, they have different electronegativity. Are you people with me?
Yes, sir.
Chlorine is more electronegative than hydrogen. Okay, so the bonding electron between hydrogen and chlorine will spend more time with chlorine than with hydrogen. As such, chlorine will be more partially negative, and hydrogen will be partially positive. This is what we mean by dipole. Dipole results as a difference in electronegativity. Okay? So this dipole also creates a sort of attraction between the molecule of a substance. One of the effects of dipole is dipole moment. A phenomenon known as dipole moment. Okay? And this example we gave here is that of a compound containing halogen or an electronegative element, such as nitrogen, oxygen, chlorine, or bromine. Any substance or any compound in which any of these elements is bonded to carbon, you expect a dipole between the bonds. As such, if there's a dipole moment will occur. And dipole moment, as we have defined here, is the magnitude of the charge multiplied by the distance of the bond between the carbon and the electronegative atom. That will give you the dipole moment for that compound. And here you can see dipole moment of different molecules. Okay? For example, you have aminomethane here, or methylamine. Methylamine, the dipole moment is 0.2 dBi. This is ether, dimethyl ether. The dipole moment is 0.7 dBi. You notice that the dipole moment in ether is greater than that of methylamine. This will be as a result of electronegativity of oxygen and nitrogen. Differences in electronegativity of oxygen and nitrogen. Oxygen is more electronegative than nitrogen. That is one. Secondly, you can see that here, the oxygen atom is bonded to 2 carbon atoms. Okay? So you have dipole moments on each side of the bond. If you look at that of iodomethane, this is iodomethane, in which carbon is bonded to iodine. The dipole moment is 1.2 dBi. Okay? You can see it is greater than that of where you have oxygen, and so on, like that. Okay, if you notice here, fluoromethane has the highest dipole moment. I hope you can see it.
Yes.
Yes. This is because fluorine is the most electronegative. So yeah, it has the highest dipole moment. So in a molecule in which there's a dipole moment, there will be attraction between the opposite charges. The negative end of one molecule will attract the positive end of another molecule, bringing the molecule together. Okay? This dipole moment is one of the intermolecular forces that can operate in molecules, especially those molecules containing electronegative elements. Okay? Then we talk about dipole-induced dipole. Dipole-induced dipole. In this case, let me use this diagram for illustration. If you look at this diagram here, this is an atom, a neutral atom in which you have electron rotating around the nucleus. The electron is in constant motion. We have mentioned that before, right? It happens that at a particular point in time, the electron will be concentrated at one end of the atom, as you can see here. This concentration of electron on this end is temporary, it's not permanent. It only happens at some point in time. So at that point, this end of the atom will be electronegative, will be negative. As such, it will be attracting the other end of another atom, which is positive at that particular point in time. So at that point in time, there will be attraction between the molecules of the atoms. At that point, there's attraction, they will come close together. This coming close together is not permanent, because when the electrons shift away, they will go, each of the molecule or the atoms will go their own separate way again, until that time comes again when they attract each other. These are temporary attraction. We call these van der Waals forces. These van der Waals forces also operate in molecules, especially in non-polar molecules like alkanes, alkynes. Okay? So this type of intermolecular forces that operate in those molecules. Then you also have what we call dipole-induced dipole. Dipole-induced dipole. In this case, you have a neutral species, a neutral molecule, or a neutral atom, like what we have here. Are you with me, please?
Yes, sir.
Like what we have here. This one is neutral. If this come in contact with a dipole molecule, that is dipole, in which one is, who is that making noise now? Can you? Okay. when this come in contact with a dipole molecule, it will generate a dipole in the neutral molecule, like what you have here. Now, the positive end will now attract the negative, will let the negative concentrate on one end and positive concentrate on another end. At that point in time, the positive end of the dipole will attract the negative end of the somewhat neutral molecule, and they will come together. When they come together, there'll be attraction between them. At that point in time, we say they have dipole as well. Noise is coming from somebody. Who is that? Okay. So this is what we call dipole-induced dipole. You have a dipole molecule inducing polarity in a somewhat neutral molecule, thus attracting each other together. Now, so far, we have talked about three types of intermolecular forces. We talk about dipole moment. We talk about induced dipole. Then we talk about dipole-induced dipole. Okay. Then the other one is the hydrogen bond. Hydrogen bond. Hydrogen bond operates in molecules in which either oxygen or nitrogen or fluorine is bonded to hydrogen atom. If you have nitrogen, oxygen, nitrogen, or fluorine bonded to a hydrogen atom in any molecule, then hydrogen bond will operate. And what happens is that the hydrogen of one molecule will attract the negative atom or electronegative atom of another molecule. For example, if hydrogen is bonded to oxygen, oxygen of one molecule will attract, this is it here, oxygen of a molecule will attract the hydrogen end of another molecule. This type of attraction is what we call hydrogen bond. Okay, you can see that this is another hydrogen, also going to attract another oxygen of another molecule. Similarly, this oxygen will also be attracted to hydrogen of another molecule, and so on like that. And that is how it goes about. In molecules that hydrogen bonds operates, you find out that it affects the property of that molecule. Okay. Now, so far we have discussed 4 different types of intermolecular forces of attraction. We talk about dipole moments. We talk about dipole-induced dipole. Okay. We talk about dipole-induced dipole, and we talk about hydrogen bond that can operate in a molecule that will affect the physical properties. Now, another factor that affects property of molecule is the shape of that molecule. The shape of the molecule. Let me come here. This can be illustrated with these 4 molecules. If you look at these 4 different molecules, they belong to the same compound. Okay, we call these isomers. Look at this one here. This is N-butanol. Okay, N-butanol. That's normal butanol. This one is secondary butanol. This is isobutanol. And this is tertiary butanol. Another name for tertiary butanol is 2-methyl-propanol. Another name for secondary butanol is 2-methyl-propan-1-ol. While secondary butanol is 2-butanol. Then you have the normal butanol. You can see that the difference between these, they have the same number of carbon atoms, the same number of hydrogen, the same number of oxygen. But what makes the difference is the way the atoms are joined together. Okay? The way the atoms are joined together. They are isomers, of the same compound. Now, this shape, this one is a straight chain. There's no branch here. The molecules of this straight chain butanol, when they align together, they can come very close. So they will fit tightly together, such that to break them apart, you will need a lot of energy to break them apart. But if you look at secondary butanol, it has a branch. They cannot come closer to each other as the normal butanol can come close to each other. Their closeness will be limited. So they will require less energy when you compare it to normal butanol. The same thing goes for isobutanol. Okay? And if you consider or compare them with tertiary butanol, you can see that this one has a lot of branches, many branches. So the molecules can come very close to each other. They can come very close to each other. Such to break them apart will be very, very easy. This is how shape of the molecule also affects the property. If you, for example, if you consider their boiling points, normal butanol we have the highest boiling point, while tertiary butanol we have the lowest boiling point. Okay? And this is illustrated in this table as you have it here. We have the butanol here, normal butanol, isobutanol, tertiary butanol, and secondary butanol. If you compare their boiling point and melting point, you notice that normal butanol has the highest, while tertiary butanol has the lowest. This is how shape affects the properties. Another example here is this compound. They are known as fatty acids. The first one here is the oleic acid, while this one is stearic acid. If you look at stearic acid, it's a straight chain fatty acid. While in oleic acid, it is not branched, but you have a double bond. It is unsaturated. And because of the double bond, you can see how the molecule look at. The structure become distorted, unlike stearic acid, which is regular. It is regular. So when the molecule of stearic acid come together, when to want to arrange them together, they can fit perfectly together. But in the case of oleic acid, because of the double bond, they can't come very close, as with stearic acid will come very close. And as a result of that, we notice that the melting point of oleic acid is 16 degrees Celsius, while the melting point of stearic acid is 70 degrees. You can notice the difference between the two, 70 to 16, because of the structure. In fact, stearic acid is solid at room temperature, while oleic acid is liquid at room temperature. And these two compounds is a compound all of you have been eating since you are born. Do you agree with me? These two compounds, they are compounds you have been eating. Oleic acid is your groundnut oil, while stearic acid is fatty, more or less butter or fat. Okay? Yeah, you all know that, except in the what you call it, unusual situation, groundnut oil are always liquid. No matter the condition, they do not solidify. Am I right or wrong? Is that not correct? I'm sure you will agree with me. Okay, so we have mentioned 5 factors that affect properties, physical properties of organic compound. We mentioned which one? Dipole moment, isn't it? We mentioned dipole forces. induced dipole forces, hydrogen bond, and molecular shape. These factors determine whether a molecule will boil at high temperature or at low temperature, whether a molecule will melt at high temperature or at low temperature, and so on and so forth. Okay, before I go further, let me give you some time if you have query for me. If you have question, you can ask your question now. You like to unmute yourself to ask your question. And if there's no question, yes.
Sir, I have question. My question is, you said the factors affecting structure and physical properties. The first one you said is intermolecular force.
No,
Then
the first one is not intermolecular force. What I said was that intermolecular forces that operate in a molecule will affect the property of that substance. That is what I said. Okay?
Okay.
And those intermolecular forces are the one I've just highlighted. Dipole moment, dipole forces, induced dipole forces, hydrogen bonds. Those are intermolecular forces.
Van der Waals forces included, sir.
What?
Van der Waals forces.
Van der Waals, yes. Van der Waals forces comprises of dipole and induced dipole forces. They are both Van der Waals. Okay?
Yes, sir.
Yes, any other person with any other question? If there's no other questions, can we then go on?
Yes, sir.
No question?
No question, yes, sir.
Okay. If there are no questions, then we can continue. Let me share the screen again. Okay. One of the physical properties is the viscosity. Okay. Viscosity is a measure of how much a liquid resists flowing. Okay, viscosity of a compound. How easy a liquid can flow. And you can understand this if you compare water and honey. Water or honey. Okay? If you pour water and pour honey, you can also practicalize this and see how easy you can pour the two. That will tell you what we mean by viscosity. You notice that honey is more viscous than water. You can also experiment this. You can carry out this experiment. Put two different types of liquid into a container. Okay? Into container and drop something in it. Okay? The most viscous of the two liquids. Okay, so the object you drop will not go down as fast. The one that is more viscous will resist the going down of the object, while the one that is less viscous, the object can go down easily. You can try it and see the result yourself. That's what I mean by viscosity. And if a compound, a substance is viscous, it means the intermolecular forces are very strong. They are very strong. That is why it holds the molecule tightly together to make the substance a viscous one. So viscosity is one of the physical properties that are affected by intermolecular forces. Density is another one. From your primary school or secondary, you know that density is simply mass per unit volume. Okay? Substances in which you have very strong intermolecular forces will be more dense than those in which intermolecular forces are weak. Okay? For example, stone. We all know that stone is a very dense object. Okay? When you talk about liquids, we can use density to separate liquids as you have it in this diagram. Look at the diagram in this measuring cylinder. We have different liquids here. This one is orange, isn't it? This one looks like red. This one is green. And this one seems to be black also. We are able to see these different liquids at different layers because of their density. The one that is more dense is at the bottom, and the density decreases as you go up. This one is the less dense among the liquids. Also, if you have a liquid and you want to, let's say you have water in 3 jars, you have to examine the density of 3 objects. Just throw them in 3 different jars. Notice how they will go down the vessel or the container. The one that goes down easily is the one that is more dense. The one that cannot go down is less dense. The one that is flowing on top of the liquid is a very less dense object. Okay, so we have talked about density, another physical property of compounds. Then we talk about melting and boiling points. Melting and boiling points. Objects in which, or substances in which you have strong intermolecular forces, you will need more energy to break them apart. Such substances will have high boiling points. While those that have weak forces of attraction will boil at low temperature. The same thing applies to melting points. The stronger the intermolecular forces, the higher the melting point, the higher the boiling point. The weaker the intermolecular forces, the lower the melting point, the lower the boiling point. And this is illustrated in this table here. I believe you can all see this table. If you look at ethane, in ethane, it's only dipole, induced dipole, that is operating. And it has a melting point of -183, boiling point of -89. And it is a gas at room temperature. Dimethyl ether, you have dipole operating in dimethyl ether. Okay? And in dimethyl ether, where again? I think. Okay. Dimethyl ether, though it has a very low melting point, low boiling point, -141, -24, but it's a gas at room temperature. But the melting point and boiling point is higher than that of ethane. This is because in ethane, the intermolecular forces is weaker when you compare it with the dimethyl ether. Induced dipole is weaker than dipole. Consider chloroethane. Chloroethane. The melting point is higher than that of dimethyl ether. Also, the boiling point is higher, though it's also a gas at room temperature. But because, if you consider dimethyl ether and chloroethane, the same intermolecular forces is operating in the two. But if you consider the two, chlorine is the electronegative atom in ethane, that is attached to ethane, while in dimethyl ether, you have oxygen as the electronegative atom. Chlorine is more electronegative than oxygen. So the dipole that's operating here is stronger when compared with dimethyl ether. And that is why chloroethane has higher melting point and higher boiling point. Now let's go to pentane. In pentane, it's just in this dipole that is operating, because pentane is also an alkane, a non-polar molecule. It has the boiling point is -130. It is higher than that of ethane. The boiling point is 36, higher than that of what do you call it? Ethane. Also higher than that of dimethyl ether and higher than that of chloroethane. Now, and it is liquid at room temperature. This is because in pentane has 5 carbon atoms. It has 5 carbon atoms. The number of carbon atoms is more than that of ethane, which has 2. It is more than that of dimethyl ether, which is also 2. It's also more than that of chloroethane, which is also 2. The higher the number of carbon atoms, the stronger the intermolecular forces, because the molecule will be able to come to very close together, and the number of electrons also increases. So this will increase the strength of the intermolecular forces. That is why ethane has higher boiling point and higher melting point. Propan-1-ol. Propan-1-ol has just 3 carbon atoms. Okay, and it has higher melting point, higher boiling point. This is because, apart from the fact that you have dipole in propan-1-ol because of the oxygen atom, you also have hydrogen bonds that is operating. And hydrogen bond is a very strong intermolecular. This, because of the stronger intermolecular forces, the strength of attraction between the molecule is high, and you require higher energy to break them apart. That is why propan-1-ol boils at a very high temperature and melts at very high temperature. The same thing goes with ethanol, when you consider ethanol, butan-1-ol, and ethanoic acid. In ethanoic acid, which has just 2 carbon atoms, but it is ethanoic acid. In ethanoic acid, you have 2 carbon atoms. You have dipole operating in ethanoic acid, and you also have hydrogen bonds. Okay, but the difference between ethanoic acid and propan-1-ol, or the alcohol, is that in ethanoic acid, you have 2 types of hydrogen bond that is operating. 2 types of hydrogen bonds. You have what you call intermolecular hydrogen bond and intramolecular hydrogen bond. Okay, intermolecular hydrogen bond and intramolecular hydrogen bond. More energy will be required to break this hydrogen bond apart, and that is why ethanoic acid boils at very, very high temperature and melts at high temperature. Unlike the alcohols, in alcohol, only intermolecular hydrogen bond is operating. Okay, when you compare alcohol and ethanoic acid, in ethanoic acid, you have 2 types of hydrogen bond, intermolecular and intramolecular. But in alcohol, it's only intermolecular hydrogen bond that is operating. And that is why ethanoic acid has very high boiling point and high melting point. Okay. Flammability is another property. And flammability is a measure of how easy it will be for a substance to catch a light and burn. How easy you can ignite a substance. Flash point is another substance, another property, which is related to flammability. And flash point is the lowest temperature that is likely for a substance to form gaseous mixture that can be ignited. Okay? This also is affected by intermolecular forces. The one that is high flammable, they are very weak, what do they call it? Very weak intermolecular forces. If substances have weak intermolecular forces, it will have it will be easily ignited because it can easily form gases that can be ignited. Okay. There is another property that is related to flammability flash point, and that is vapor pressure. Vapor pressure. All this we have discussed, I think we discussed in one of the lecture. The vapor pressure is the pressure exerted because when you have substances, if you have substances in liquid, like for example, I have a liquid in this mug. Okay, in this liquid we have here some of the molecules of the liquid will be at gaseous phase on top of the liquid itself. Those one on the gaseous phase will be exerting some pressure on the whole liquid. It is this pressure that is referred to as vapor pressure. Okay, that is referred to as vapor pressure. If you have very weak intermolecular forces, the more of the molecule will be in the gaseous phase, and we exert very high pressure. So the vapor pressure will be very high. So substances with weak intermolecular forces, we have high vapor pressure. While substances with with strong intermolecular forces, we have low vapor pressure. Okay, this is what is explained here. And this is also illustrated, as you can see here. In the first diagram here, okay, this substance, water, has few molecules in the gaseous phase. It has few molecules in the gaseous phase, so it has low vapor pressure. This one has relatively high molecule, that is ethanol. So it has higher vapor pressure than water. While propanone has very high molecule in the gaseous phase and has very high vapor pressure. If you consider them again, water has hydrogen bond. It has strong intermolecular force. Ethanol also has hydrogen bond, but the intermolecular force, it also has carbon atom, 2 carbon atom. Water has no carbon atom. The carbon atom, they are non-polar, so they reduce the strength of the hydrogen bond, the attraction of the hydrogen bond. Another way you can look at it is that if you look at the molecule of oxygen, this is what is pictured here. This is, molecule of water. Look at water here. You have oxygen attached to 2 hydrogen atoms. Okay, each of these hydrogen atoms can form hydrogen bond with another water molecule. And this oxygen can also attract another hydrogen atom from another molecule. But consider with ethanol, this is oxygen of ethanol here, and this is the hydrogen. Here, only 1 hydrogen is attached to oxygen. So you can see why the strength of hydrogen bond in ethanol is less than that of water. And that's why the vapor pressure is high. And we look at propanol. These are propanol here. Okay, propanol. The oxygen in propanol has no hydrogen. It's not attached to any hydrogen atom. So there can be no hydrogen bond in propanol. So the intermolecular forces here is weaker when you compare it with ethanol or water. And that is why it has a very high vapor pressure. Okay? And this table also gives us a summary of the flammability, vapor pressure, and flash point of different substances, depending on their intermolecular forces. Okay? Before I go further, let me pause here for you to ask questions if you have any. If you have any question, you can ask, please. Any question? Time for us to ask a question now. Yes.
There's a question.
Okay, yes, go ahead.
In a thing, in boiling point, we have one at minus 183. Why is boiling point is minus 89, which is gas? But so I was confused. How is it in methane? The figure there are lower than the one of methane in ethane, which is liquid. Is it because it's liquid? That's why they have the higher boiling.
What is the figure for ethane and what is the figure for pentane?
The figure for ethane is minus 183.
Okay. Pentane.
So that the one of pentane is minus 130.
Okay. The one you have just mentioned, is it the boiling point or the melting point?
Yeah. Boiling point.
Okay. For ethane is 183. For
yes.
For pentane is minus 130. Now, which one is higher? Minus 183 minus what?
Because you said ethane is higher than, you said pentane is higher than ethane.
Yes.
And in the figure are different.
Yes. No,
because you can take a look.
Wait a minute. I know why you are confused. Why you are confused that you have minus 183 and minus 130. Isn't it?
Yeah.
Now,
yes, sir.
Between minus 183 and minus 130, which one is larger?
183 is larger.
That is why you get it wrong. It is minus 183. Minus 183, minus 130. Minus 130 is greater than minus 183.
How, sir?
Because look at it this way. You have a, let me try and how do I, if you have zero, okay, let me ask you, between minus 183 and minus 130, which one is closer to 0?
130.
Minus 130 is closer to 0. Okay?
Yes, sir.
Minus 130 is closer to 0.
It's closer to 0. Now, if you are going from minus 183 to minus 130, which is closer to 0, are you going up or you are going down?
From 183, we are going down.
To 0. After 0, what do you have?
It will be negative again, which is point.
No, wait a minute. After 0, what comes next after 0?
Any number after 0 is minus.
From minus, we are going from minus. I get to 0. The next one will be what?
1.
Is it minus 1 or plus 1?
minus
Plus.
1.
Plus.
Is it minus 1 or plus 1?
Plus 1.
Minus 1, sir.
Plus 1, not minus 1. Now, do you now say that from 0 to plus 1, is it going up or going down?
From 0 to plus 1, I mean.
Yes. Going
up.
Going up.
Yes.
Now, from minus 130 to minus 120, are you going down or going up? You understand? I'm trying to look for how I can illustrate this so that you can be able to see it clearly. Okay, I saw something here now. Now, I'm going to share this with you so that you'll be able to see what I'm talking about. Where is that? Okay, this is it. Let me share this with you. Can you see this line number?
Yes.
Now, this one does not portray what I'm looking for. Okay, let me see. Maybe you'll be able to understand using this one now. Let me use this one. This one starts from 0. I hope you can see it. It goes from 0 to 15. When we move from 0 to 1, is it increasing or decreasing?
It's decreasing.
Now, if you go from 0 to minus 1, increasing or decreasing?
Increasing.
Increasing or decreasing?
From 0 to 1.
To minus 1.
Yes.
From
From
minus
0
1
to 1.
Is increasing.
From 0 to minus 1. Is it
it's
increasing
decreasing.
or decreasing?
It's decreasing.
It is
decreasing.
Decreasing. Now,
yes.
Look at it. From minus 1 to
From
minus
0 to
130.
minus 1.
Are you going up or you are going down?
Okay, I understand now. It's going up.
From minus 1 to minus 130. Is it up or down?
Up.
It's down. It's not increasing. It is decreasing.
Yes.
Okay.
Do you get it now? From
yes.
minus 1 to minus 130. Is it increasing or decreasing?
It's decreasing.
It is decreasing.
Yes.
I hope you can all get it. It is decreasing. So if you now say you move from minus 130 to minus 120, from minus 130 to minus 120, is it increasing or decreasing?
It's decreasing.
Minus 130 to minus 120. Increasing or decreasing? It is what?
It's decreasing.
Increasing.
No,
it is
decrease.
It increase. It increase. If you move from minus okay, from minus I'm coming. This is what I'm looking for here. I'll give me negative something. Okay, let me see this one. Hold on. Okay. Can you see the screen again or you cannot see it?
It's not showing, sir.
Okay. Let me try and find what I'm looking for so that I can be able to show you that. Okay, let me see if this one will help. So that you'll be able to understand what we are talking about. Okay, now let's see. Let me go back to, let me share this. Now, can you see this one?
Yes.
Now look at this line number here. Okay, look at 0. From 0 to 8. On your left-hand side, you have +1, +2, +3, and so on. Isn't it?
Yes,
Is that not?
Yes.
And on the right hand, you have -1, -2, -2 up to -8. Isn't it? Now look at it. Take 0 as our origin. If you move from 0
yes, sir,
to +1, is it increase or decrease?
It's increase.
If you move from 0 to -1, does it increase or decrease?
It's decreasing.
Now, if you move from 0 to -8, does it decrease or increase? Increase or decrease?
Decrease. 0 to -8.
Decrease.
Now, if you move from -8 to -7, is it increasing or decreasing?
Increasing.
Is what?
Increasing.
It increased. Ajimati, what are you eating?
I'm not eating anything.
It increased.
Yes.
Okay, from -7 to -6, increasing or decreasing? It increases?
Increase.
Okay, now let us visualize it. We have I figures. Assuming here we have -180. This is -170, -160, -150, and so on like that. If you now move from -180 to -130, does it increase or decrease?
Increase.
It was what?
Increase.
It increased. So 183 minus 183 is less than -130. You now understand? You understand now?
Yes, understood.
Any other question? Another question, please. If there's no other question, shall we continue then?
Yes.
Okay. Another property here is solubility. Okay. The solubility of a substance also has to do with the intermolecular forces, especially hydrogen bond. When we are talking about solubility, we are talking about solubility in water. Okay. Molecules that can form hydrogen bond will be highly soluble with water because they will be able to overcome each other. This is how we explain solubility. In this first diagram here, the substance here is highly soluble. Here, you have some particles. We say it is sparingly soluble. And here, it is insoluble. Because all the particles settled at the bottom of your container. This one, it is insoluble. This one is sparingly soluble. And this one is soluble. Okay, this is just an illustration of solubility. Okay. Now, so far we have said dipole moment, van der Waals, hydrogen bond, and shape of molecules affect the shape, the physical property and structure of molecules. Physical, and when we talk about physical property, we're talking about the density, viscosity, boiling point, melting point, flammability, vapor pressure, solubility. Okay, this is what we have been discussing so far. And I ask you to practice this exercise. I don't know if you have attempted it. How many people have attempted this one? Have you done it?
Yes, sir.
You have done it. Anyway.
Yes, sir.
And this one as well. These questions.
Yes. Yes.
It's okay.
Yes.
Now, let me quickly rush over the second aspect, which is this one. In the second aspect, we explain further on the physical properties of organic molecules, especially how these affect the functional group of molecules. Okay, we have all this one. We talk about alkanes, how the physical properties affect alkanes. Okay, and here we said that look at this information here. We said increase additional methylene group increases the area of contact between the molecules. This is where we started. If you look at the homologous series of alkanes, you see that boiling point of alkane increase as their size increases. Okay, as the size increases, boiling point also increases. Okay, this is because as the number of carbon atoms increases, the area of contact between the molecule also increases. This is why the boiling point increases as the molecular size increases. And we argue that the four smallest alkanes, they are gas at room temperature. Pentane is the smallest alkane that is liquid at room temperature. And you have this table to clarify that. This is the first starting alkane from methane to tridecane. Okay, and if you compare their boiling point, we notice that it increases. Okay, the melting point also increases, but it is not as regular as the boiling point. This irregularity in melting point is explained later. Okay, it is explained here. In the melting point of alkane, because of packing, you have irregularity in the melting point. And when we talk of packing, alkane with even number of carbon atoms can pack very well, while alkane with all the number of carbon atoms do not pack very well. So alkane with all even number have higher melting point than alkane with odd number of carbon atoms. And that is why the melting point, as earlier mentioned, is not regular. Okay. We also talk about the density. Density increases with increasing molecular size. The same thing goes for the flash point. Then another factor, we have mentioned that before, is the branching. The degree of branching also affects the property of molecule. For instance, if you look at pentane, we have three isomers of pentane: the normal pentane, isopentane, and neopentane. And if you look at their boiling point, you notice that pentane, the normal pentane has the highest boiling point, while neopentane has the lowest boiling point because of branching. It's not straight. Here, the molecule come very close together. You need more energy to break them apart. Here, they can't come very close. So you need less energy to break them apart. That is why neopentane has the lowest boiling point. Then we talk about alloalkanes. Alloalkanes are also known as alkyl halides. These are compounds in which you have halogen attached to carbon atom. Like here you have methyl chloride, or we call it chloromethane. This is dichloromethane, trichloromethane, tetrachloromethane. Okay. In alkane, sorry, alloalkane or alkyl chloride, if you look at it, you have carbon bonded to chlorine in this one, for example. Apart from the dipole interaction that we are operating, you also have, sorry, van der Waals that we are operating. You also have dipole as a result of chlorine being bonded to carbon. This bond will be polarized. Carbon being partially negative, sorry, partially positive, chlorine being partially negative. So you have dipole interaction that we operate of alkane as illustrated here. Okay. Also, another factor here you need to take into consideration is the electronegativity of the halides, fluorine, chlorine, and bromine. Fluorine is the most electronegative atom. Of all the atoms, chlorine is the most electronegative. Okay, so when you consider the halogens, fluorine is the most electronegative, followed by chlorine and bromine, and so on like that. Okay, so here, the one that has the highest electronegativity, we have the highest dipole interaction. Okay, so this fact, you need also to take into consideration when you are considering their properties. Okay. Let me go to the next slide. So the nature of the halide in your compound will affect the melting and boiling point of the compound. Like we said, they are not of the same electronegativity. Fluorine, which is more electronegative, will have a stronger attraction. Okay, as such, we require more energy to break the molecules apart. So molecules in which fluorine is attached to the carbon atom, we have higher boiling point, higher melting point. Okay. Another factor is that the more the number of halogen atoms, the higher the interaction between the molecules, and the higher the intermolecular forces, the higher the boiling point, the higher the melting point. As you can see in this table, in this attached table, you have chloromethane. It has only one chlorine atom. It has this melting point and this boiling point. You have dichloromethane, which has two chlorine atoms. You can see that the melting point has increased. Similarly, the boiling point has also increased. And as you go down like that, trichloromethane to trichloromethane, the melting point increases, the boiling point also increases. Okay, and this one also shows the relative comparison between the electronegative, the halogens. Let me use methane as an illustration. This is methyl CH3. If the fourth atom to bond to is hydrogen, that means you have methane. Okay, it has a boiling point of minus 161.7 degrees. When you change the hydrogen to fluorine, the boiling point has increased to minus 78. When you change it to chlorine, it has increased to minus 24. When you change to bromine, it has increased to 3.6. And when you change to iodine, it has increased to 42, like that. Also, let me take fluorine here. If you go down to fluorine, here when we are considering this row, we are considering the change in atom from hydrogen to iodine. But if you consider this column, we are considering the increase in number of carbon atoms. Here we have one carbon atom. Here is two carbon atoms. Here it is 3. Here it is 4. Here it is 5. Here it is 8 carbon atom. This one is 8 carbon atom. And you can see that also the boiling point also increases as the number of carbon atom increases. Okay? All these differences in the number of carbon atom or the nature of atom or the nature of the atom is a result of difference in intermolecular forces of attraction. Okay. Also, branching also affect the physical properties. If you look at this one is bromobutane. Bromobutane. This one is 2-bromobutane, and this one is 2-methyl 2-bromopentane. In all these three, they have the same number of carbon atom, same number of hydrogen, same number of bromine. But you look at the boiling point decreases as you go down. This is a result of branching that prevents maximum interaction between the molecule. Okay? Similarly, alkyl halides are sparingly soluble in water because they don't operate, there's no hydrogen bond in alkyl halides, but they are soluble in organic sulfate. Now let us consider ether. Ether is when you have two alkyl groups separated by oxygen atom, or alkyl and aryl group separated by oxygen, or two aryl group separated by oxygen. These are ether molecules. In ether, we have van der Waals and dipole interaction. Okay, so ethers, they have high boiling point than alkanes and alkyl halides. Okay, and also their boiling point or melting point also increases as the number of carbon atom increases. Okay, their miscibility with water is like that, those of alcohols. We are coming to alcohol very soon. Amines are organic compound in which you have nitrogen atom attached to a carbon atom. In fact, you can consider amine as ammonia, in which one of the hydrogen in ammonia has been replaced by an alkyl group. Like what you have here. This one, we call it primary amine because one of the hydrogen has been replaced with alkyl. Here, you have secondary amine, in which two alkyl groups have replaced two hydrogen atoms. And you have the tertiary amine, in which three alkyl groups have replaced the three hydrogen atom in amine. Now, if you compare the three amines, you notice that in primary amine, it has two hydrogen atoms that are bonded to nitrogen. So you expect hydrogen bond to be operating in primary amine. Similarly, if you look at secondary amine, you have one hydrogen atom bonded to nitrogen atom. Also here, we have hydrogen bond operating. But if you compare primary amine and secondary amine, okay, the nature of hydrogen bond in primary amine will double that of secondary amine, because in primary amine you have two hydrogen. In secondary, you have just one hydrogen. Okay? Whereas in tertiary amine, there is no hydrogen bonded to nitrogen. So in tertiary amine, there will be no hydrogen bond, but you have dipole operating. Dipole and also induced dipole and so on like that. And okay. So when you compare the boiling point and melting point of amines, they are higher than those of ethers, higher than alkyl halides, and higher than alkanes. Because in amines, you have hydrogen bond that is operating. Okay, and also here, if you compare the different type of amines, the primary, secondary, and tertiary, compare their boiling point, you notice that the tertiary has lower boiling point. One, it has no hydrogen bond. And two, because of interaction, branching also affects it. Look at secondary amine. There's branching in secondary amine as well, but it has hydrogen bond. That is why it has higher boiling point than tertiary. In primary amine, the number of hydrogen bond is double that of secondary. And that's why it is also has higher boiling point. Okay. The solubility of amine also follow the same trend. Because of the hydrogen bond, the lower amines are miscible with water, okay, are more soluble than ether or alkyl halides. And this figure here illustrates the hydrogen bond in amine. If you look at this molecule, this is hydrogen bond between two amine molecules, okay? And here you have hydrogen bond between amine and water molecule. This is just illustrating what we mean by hydrogen bond, okay? Then alcohol. We also consider alcohol to illustrate the physical properties. In alcohol, you have the hydroxy group bonded to carbon atom. As you have in methanol, or this is methanol here, or ethanol, okay? In which you have hydroxy. Now, since you have hydroxy in alcohol, you also expect hydrogen bond to be operating here. So because of the hydrogen bond, alcohol are miscible with water, okay? But as the chain of the alcohol increases, the solubility in water decreases because the carbon chain will resist solubility in water, okay? Also, branching. We have been talking about branching. The branching also affects solubility as well as the boiling point. Alcohols with branched alkyl groups are more soluble in water than alcohols with non-branched alkyl group with the same number of carbon atoms. Branching minimizes the contact surface of the non-polar portion of the molecule. As a result, tertiary butyl alcohol is more soluble than butyl alcohol. Okay. This is illustrated. Okay, we don't have. I think the illustration I'm talking about, we saw it earlier. I don't know where we have where you have pentane. We also have pentanol, isopentanol, and the like. This also shows the solubility or how branching affects solubility of alcohol. And here we illustrate the hydrogen bond between water and an alcohol. Okay, and it's also possible for alcohol to form hydrogen bond with itself and also with water. This table here illustrates the solubility, or sorry, the boiling point of the first 11 alcohols from methanol to dodecanol to dodecanol. You can see the boiling point, the trends in the boiling point of the alcohols. And this table here compare the boiling point of alkanes ethers, alcohols, and amines. And you notice that in all, the alcohols have the highest boiling point. As a result of their hydrogen bonding, as well as dipole, other intermolecular forces, which others don't have. In amines, there is hydrogen bonding, but the strength of the hydrogen bonding in amine is not as strong as those of alcohol. That is why alcohols have the highest boiling point. Okay, and this one, the next two chart summarizes all what we have been discussing all along. And in a nutshell, this is what the two video sent to you. This is what is discussed. The two video, this is what we have discussed in the two video. I hope we are at home now with our illustration and explanation so far. Any question, please? Any question? Abdulkudus Assis? Yes, any question, please? Yes. Question, please. Is there no question? We should call it a day. Yes, please. Question. Paul, any question?
There's no question for now, sir.
We are not?
Yes, sir.
Question.
I don't have any question.
Abdurrahim, Abdulkadir.
Yes, sir.
Any question?
Thank you very much.
I don't think there's no question. But, sir, I want to ask for something.
Yes, I'm listening.
The thing is, we are really appreciate the way you are attending to us, and God will bless you. But I want to ask a favor from you.
Yes.
So, the thing is, the video that you are sending on the Google Classroom.
Yes.
So, I don't think all of us are able to be watching that video because the thing is consuming a lot of men. And the note
Sorry,
that you said,
I didn't get that last part. The thing is what?
The thing is consuming a lot of data, sir. I don't think many of us are able to be watching the full video, sir, including myself. So, but and the note that you send on the platform also. So, the thing is, what I think is that since the video and the note is PDF something, so I think if you can help us to be sending it on the group, so it will be
send it on what?
Now that we have the
Sorry, let me get to you clearly. I can't hear you anymore. Abdurrahim has done.
Sir. Sir.
Yes.
She's talking about the Google Class because of the notes was in PDF.
That we can
go
through it
in
WhatsApp group. What I'm trying to say is that if we can.
He has gone again. I heard him again. Now, okay, he said I
he's
should
talking about
the notes on WhatsApp.
On the group. That's what he's trying to say.
The notes. Yeah, now there are two things. There are two different things entirely. He said because of data, the video.
Yes,
I mean, you people are not able to get the video.
Yes, sir.
Is that not?
Yes.
Now, but the note itself, you can easily get that one from the Google Classroom. That one will not consume more data than the video.
Yes, you can get the note.
Are you now saying that I should not make any video again? I should just be sending the notes to you. I'm asking a question.
I think I can try to explain what he meant.
Hold on. Who is talking?
Rihanna.
Okay, yes, go ahead. Rihanna, go ahead.
Sir?
Rihanna.
Yes, sir.
Yes, you are trying to say?
I think what he's trying to say is that the video you uploaded on the Google Classroom, that one is consuming data because we have to access it through YouTube. That's number one. And the other one, he said, since the note is in PDF form, that why are you not sending it in our WhatsApp group instead of that Google Classroom? So I think that is what he's trying to say.
I'm now saying that, one, the note, if you access it from the Google Classroom, okay, what difference will it make if you access it from the WhatsApp? Will it make any difference?
Sir, there is difference, sir.
What difference?
The difference is that in the Google Classroom, if you are not connected to our data service, we cannot access it anytime. But if it is PDF, sir, we would have downloaded it and we can always access it anytime. That's the difference.
You can also download it from the Google Classroom as well. It is downloaded.
It is not going, I have tried it.
Try it a lot. Not going.
Try it.
So if you are not connected, it won't bring it. Even if you are downloaded.
You see, when you access the first time,
try it again.
You can download it. It's like Paul has been able to download it before.
Yes, I've downloaded at least the first and the second one.
I tried to do that too without connection. It is because the thing is, we direct us to our Google Drive, and one cannot access Google Drive without data, without being connected.
Yes, you can download anything from Google Drive.
You download it directly from that Google Class.
But it's not going. That is what I'm trying to say.
I'm talking about Google Class, so I'm talking about our Google Drive.
Yes,
I mean our drive from our different emails. That's where the note is being downloaded.
It is possible for you to download anything from Google Drive into your device. Once you access it, you can download it.
Maybe I will try that one then.
Now, as for the
I'll
video,
try downloading from my Google
for the video, making the video consume data. Uploading it also consume data. Now for you to access the video, it will also consume data. If you now said you don't want the video, then I'll stop making video. And I will send
sorry, sir. I think
to you. What?
Yeah, sorry about that, sir.
No, if
So
the
I
video
think
is
it's
not,
from his part. That's what he said. Though for someone like me, accessing that video is not a problem. But from his part, I think he's talking about himself that it's a problem.
no. Okay, if that is okay.
Hi, sir.
Any other question, please?
Sir.
Yes. Who want to talk? Is it Mary?
Yes, I want to talk about the video, sir. That it's okay like that because it is much more well explanatory. Hello, sir.
Yes, I'm listening. I get you.
Okay, I'm talking about the video, sir.
Okay.
That the video is okay like that. That it is even much more explanatory.
Okay.
Yes.
All right then. Any other question? I noticed that some people are coming in and going out of the class.
Maybe it is network.
This is network, sir.
This is the network. So, any other questions? So it's already 6 p.m. Stephen, is there any question from you?
No, sir.
Some people have mentioned that whenever we are in class, we should all of you should show your faces. A lot of people here are not showing they're not on in their camera. So that you can see you. At least you can all see me. Can't you see me? You can see my face, you can see my back. Are you still recording?
Ben, sir.
Mercy, you are welcome. You are just coming in. I've talked about you at the beginning of this class. Mercy, show your face. And yes, let us see your face too. That as somebody you admitted in the class, the person has not been participating in the class at all. And we don't know if it's part of us or not. Yes, Mercy.
Yes, sir.
The person you admitted into the WhatsApp group.
Sir?
The person you admitted into the WhatsApp group. She's not participating.
Yes. He told me he's chemistry student, so I don't know what's happening.
We asked her to introduce herself. She didn't introduce herself. She didn't say anything about the assignment we submitted, and she's not even here now. So if it's not part of us, it won't be in the WhatsApp.
I have something to say, sir.
Yes.
Actually, it's more or less a favor or perhaps a request. I don't know how to put it. Can I proceed, sir?
Proceed.
Okay, sir. Now, the other time before we started this class, there was a lecturer that came visiting at your office. He was telling you that he's supposed to have a class with us too. Please help us to fast track that process so that I can start his class soon.
It's not you. It's talking about
okay, it's not us.
It's contact 2.
Okay.
Not contact 1.
I just knew I overheard something like that.
It's with contact 2, not contact 1.
Thank you.
Okay.
Okay, sir. Thank you.
And Mercy, you have not been participating in the class. Where have you been? Mercy? I said, I noticed you are on and off.
It's the network, sir.
What happened to the network? We should have prepared
It's
for this.
fluctuating. I don't know what happened.
Maybe. Next time you have to find a location where the network is stable and strong so that you'll be able to participate very well in the class. Similarly, this girl, Aligbe, I noticed she has been going in and coming out. Or coming in and going out. And after I take attendance now, she said she was in the class. Yeah, Aligbe, you are here now. Where is she? Consider. So, when is our next meeting?
It's on Friday now.
On Friday.
Yes, sir.
Probably by Friday, we would have studied the lectures. Have you?
Yes, sir.
Yes, sir.
And get back with pile of questions. Okay?
Okay, sir.
So Friday, what time?
I think it's 5.
Is it 5 or 4?
Friday,
on timetable, I think on that timetable.
5. I have lecture 4 to 5. Okay?
Our own is 5. I think 5:37.
Our own is 5. I think 5 or 5:30.
5:30.
On the timetable.
The lecture will start by
5:30. Thursday, sir.
What?
Thursday
No.
or what?
It's not Thursday, it's 5. It's Friday. That's our next on timetable.
Okay, Friday, sir.
Friday.
Yes.
That is 5:30, Abby.
Yeah.
Yes.
4 to 6.
Hello.
Friday, the lecture will start by 5:30. I just told you that I have the lecture 4 to 5 on Friday.
Okay.
Yes. So if there are no other questions, then you can call it a day.
Thank you, sir.
Thank you, sir.
See you on Friday then.
Thank you.